Look at the night sky on a clear night, far from city lights. It is dark. The stars are points of light separated by blackness. Most of the sky, the overwhelming majority of what you see when you look up, is not lit by starlight. It is dark. The few bright points are islands in an ocean of black. This seems obvious. Of course the night sky is dark. There are not enough stars to light it up. But wait. The universe is approximately 13.8 billion years old. It contains between 1 and 2 trillion galaxies. Each galaxy contains, on average, several hundred billion stars. The total number of stars in the observable universe is estimated at approximately 10 to the power of 24, a septillion stars, 1 followed by 24 zeros. More stars than grains of sand on all the beaches and deserts on Earth combined, by a factor of roughly 10,000. These stars are emitting light in every direction, right now, continuously. Every star in every galaxy, in every direction you could point a telescope, is radiating photons outward into space. Light is traveling toward you from every direction simultaneously. If there are enough stars and enough directions from which light is coming, if the universe is large enough and old enough and contains enough stars, every line of sight from your eye outward into space should eventually terminate on the surface of a star. Every direction you look should show you a star. The entire sky should be as bright as the surface of a star, as bright as the surface of the sun, in every direction, simultaneously. The sky should be blazing white in every direction. Day and night should be indistinguishable, because the night sky should be as bright as the day sky. The surface temperature of the Earth should be thousands of degrees, because the incoming radiation from every direction of a stellar bright sky would heat everything to stellar surface temperatures. Obviously, none of this is happening. The night sky is dark. The Earth is not thousands of degrees. You can look at the night sky without being blinded. This is the paradox. It is called Olbers' paradox, named after the German astronomer Heinrich Wilhelm Olbers, who formulated it clearly in 1823, though the question was recognized by others, including Johannes Kepler in the early 17th century and Edmund Halley in the 18th century. Olbers did not solve it. He proposed an explanation that turned out to be wrong, but the paradox bears his name. The question is precise. The universe contains an enormous number of stars radiating in all directions. Why is the night sky dark instead of uniformly bright? The wrong answers are instructive. The first wrong answer that many people reach immediately is that starlight fades with distance. Stars far away are dimmer than stars nearby. This is true. The intensity of light decreases with the square of the distance. A star twice as far away appears 4 times dimmer. But this does not solve the paradox. Here is why. As you look to greater distances, the stars become individually dimmer, but there are also more of them. In a shell of space at twice the distance, there is 4 times as much volume of space, and therefore 4 times as many stars on average. The increased number of stars exactly compensates for their reduced individual brightness. The total contribution to the sky brightness from each shell of equal thickness is the same, regardless of distance. Adding shells to infinity adds infinite brightness. The sky should still be infinitely bright. The second wrong answer, proposed by Olbers himself, and still sometimes heard today, is that dust and gas in interstellar space absorbs the light from distant stars, preventing it from reaching us. This explanation fails because it violates thermodynamics. If dust absorbs starlight continuously, the dust itself heats up. It heats up until it radiates as much energy as it absorbs. At thermal equilibrium, the dust would be glowing at the same temperature as the stars, and the sky would still be bright as a stellar surface. The third wrong answer is that the universe is not infinite, that there are only a finite number of stars, and they do not fill the sky completely. This would solve the paradox if the universe were small enough and contained few enough stars. But this answer fails observationally. The universe is far larger than would be required to fill the sky with stars if the simple calculation applied, and we observe enough stars in enough directions to produce a bright sky if light travelled freely forever. The real answer, or more accurately, the combination of real reasons, is more interesting than any of these wrong answers, and it requires understanding two things about the universe that were not known when the paradox was first formulated. The first is that the universe has a finite age. The second is that the universe is expanding. Let us start with finite age. The universe is approximately 13.8 billion years old. This means that light from objects farther than approximately 13.8 billion light-years away has not had time to reach us. Light travelling at 299,792 kilometers per second for 13.8 billion years covers 13.8 billion light-years. Any source more distant than that has light currently in transit that has not arrived yet. This creates an observational horizon, the edge of the observable universe. Beyond this horizon, we cannot see anything, not because nothing exists, but because light from those regions has not had enough time to reach us. The universe may be infinite, but the observable universe is finite. A finite observable universe means a finite number of stars whose light has reached us, not an infinite number. A large number, roughly 10 to the 24, but finite. And while this number is enormous, it is not sufficient to cover every line of sight in the sky with a stellar surface. Think about it this way. Every line of sight from your eye outward has some probability of hitting a star before reaching the edge of the observable universe. If the density of stars and the size of the observable universe are such that most lines of sight do not hit any star, if most lines of sight extend all the way to the edge of the observable universe without encountering a star, then most of the sky is dark. The calculation confirms this. If you draw a line from Earth in a random direction, the probability that it intersects a stellar surface before reaching the edge of the observable universe is approximately 1 in roughly 10 to the power of 23. 23 orders of magnitude below certainty. Most lines of sight reach the edge of the observable universe without hitting anything. This is why the stars are discrete points of light in a dark sky, rather than a continuous bright background. The observable universe is not large enough, or old enough, or dense enough with stars for every line of sight to terminate on a stellar surface. But the finite age of the universe is not the complete answer. It explains why the sky is dark, but it does not explain why the darkness is as dark as it is, why the contribution from the stars we can see does not make the sky significantly brighter than it is. Here, the second reason, the expansion of the universe, becomes essential. The universe is expanding. Galaxies are moving away from each other. The farther a galaxy is, the faster it is receding from us. This recession produces a redshift. The wavelength of light emitted by a receding source is stretched to longer wavelengths. An object receding at 10% of the speed of light emits light whose wavelength is stretched by 10% when it reaches us. An object receding faster has its light stretched more. For very distant galaxies, the redshift is extreme. Galaxies at the edge of the observable universe are receding from us at speeds exceeding the speed of light. Not because they are moving through space faster than light, which is forbidden by special relativity, but because the space between us and them is expanding. The light from these galaxies is redshifted so dramatically that most of it is shifted out of the visible spectrum entirely, from the ultraviolet, or visible, into the infrared, or microwave, or radio range, where human eyes cannot detect it. This cosmological redshift has a direct effect on the brightness of the sky. A photon that is redshifted by a factor of 2 has half the energy per photon. The power delivered to our eyes by distant starlight is reduced by the redshift. For very distant galaxies, the redshift reduces the energy of their light so dramatically that their contribution to sky brightness is negligible, even if their light has had time to reach us. The cosmic microwave background radiation, the thermal afterglow of the Big Bang itself, is the ultimate expression of this redshifting. The hot plasma of the early universe emitted radiation with a temperature of approximately 3000 Kelvin, orange-hot, visible light. By the time this radiation has travelled 13.8 billion years through an expanding universe, its wavelength has been stretched by a factor of approximately 1100. It now peaks in the microwave range, invisible to human eyes, but detectable by radio telescopes. The entire sky is glowing with the redshifted thermal emission of the hot early universe, uniformly from every direction, but at microwave frequencies completely invisible to us. So, the complete answer to why the night sky is dark involves both factors working together. First, the universe has a finite age. Not every line of sight terminates on a stellar surface, because the observable universe, while vast, is not infinite in extent, and the density of stars is not high enough for every direction to contain a star within the observable volume. Second, the universe is expanding. The light from distant stars and galaxies is redshifted to lower energies. The most distant sources, including the hot early universe itself, have their radiation shifted entirely out of the visible spectrum. The total visible light reaching us is a small fraction of the total radiation that has been emitted in our direction. These two factors together, finite age creating a finite observable volume, expansion reducing the energy of light from distant sources, explain why the night sky is dark despite containing an enormous number of stars. But the paradox being resolved does not mean the question is exhausted. Because what Olbers' paradox points toward, the specific combination of facts about age and expansion and radiation that makes the night sky dark, is a window into some of the deepest physics in cosmology, and following each thread leads somewhere genuinely surprising. Let us start with the finite age thread and follow it to where it actually leads. The universe is 13.8 billion years old. This fact, which seems like it should simply be a historical datum, a number in a table of cosmological parameters, is actually one of the most remarkable facts in science. It was not known with any confidence until the 20th century. Before the development of modern cosmology in the early 20th century, the prevailing view was that the universe was eternal, infinitely old, always having existed, always going to exist. An eternal universe would have produced an infinite amount of starlight, and the night sky would indeed be blazing. The discovery that the universe has a beginning, a finite age, is therefore directly relevant to why the night sky is dark. We can sleep under a dark sky at night, instead of being roasted alive by stellar radiation coming from every direction, because the universe has not been producing starlight forever. It started approximately 13.8 billion years ago, and the light produced since then is not sufficient to fill the sky. How do we know the universe has a finite age? The evidence comes from multiple independent lines. The most direct is the Hubble expansion. In 1929, Edwin Hubble published observations showing that distant galaxies are receding from us. Their light is redshifted in proportion to their distance. The farther a galaxy, the faster it is moving away. This relationship, called Hubble's law, means that in the past, all galaxies were closer together. Run the expansion backward and everything converges to a starting point, a moment of extreme density and temperature from which the universe has been expanding ever since. The Hubble constant, the rate of expansion, determines how long ago this starting point occurred, approximately 13.8 billion years. The cosmic microwave background radiation provides independent confirmation. If the universe began in a hot, dense state and has been expanding and cooling ever since, the radiation from that hot beginning should still be detectable today, redshifted to microwave frequencies by the expansion. The CMB was discovered in 1965 by Arno Penzias and Robert Wilson at Bell Labs. They were initially trying to eliminate what they thought was instrument noise, and discovered instead that the entire sky was glowing uniformly in microwave radiation at a temperature of approximately 2.725 Kelvin. This is the thermal signature of the hot early universe stretched to microwave wavelengths by 13.8 billion years of cosmic expansion. The abundances of light elements, hydrogen, helium, deuterium, lithium, provide a third line of evidence. The specific ratios of these elements in the universe are consistent with predictions of Big Bang nucleosynthesis, the nuclear physics of a hot, dense, early universe cooling through the temperature window in which nuclear reactions occur. The predicted abundances match the observed abundances with extraordinary precision when the age and expansion history of the universe are used as inputs. The ages of the oldest stars provide a fourth line. The oldest stars in globular clusters, tight spherical clusters of very old stars orbiting the Milky Way, have measured ages from stellar evolution theory of approximately 13 to 13.5 billion years. A universe only 13.8 billion years old just barely accommodates stars of this age. The stars formed when the universe was a few 100 million years old. All four independent lines of evidence converge on approximately 13.8 billion years for the age of the universe. This convergence, from galactic recession rates, from the CMB temperature, from light element abundances, from stellar ages, is one of the strongest confirmations in all of science. And this age is why the night sky is dark. Not because the universe is small, it is incomprehensibly large. Not because there are few stars, there are a septillion of them. But because the time for light to travel from distant stars to us is finite and bounded by the age of the universe. Let us now follow the expansion thread and see where it leads. The universe is expanding. This fact, confirmed by Hubble in 1929, predicted by Einstein's general relativity years earlier, has implications that go far beyond explaining the darkness of the night sky. The expansion of space is not ordinary motion through space. It is not that galaxies are moving through pre-existing space like billiard balls moving across a table. It is that space itself is stretching. New space is being created between galaxies continuously. A photon travelling through this expanding space has its wavelength stretched by the expansion. The cosmological redshift is not a Doppler shift due to motion, but a cosmological stretching due to the expansion of the medium through which the photon travels. This distinction matters because it means the redshift is not limited by the speed of light the way ordinary motion is. An object moving through space cannot exceed the speed of light. But the expansion of space has no such limit. Distant galaxies can recede from us at superluminal rates without violating special relativity, because they are not moving through space faster than light. They are being carried away by the expansion of space itself. The observational consequence is that there is a cosmological event horizon, a boundary beyond which galaxies are receding so fast that their light can never reach us. This horizon is not at 13.8 billion light-years, but at approximately 46 billion light-years, the co-moving distance accounting for the expansion of space during the 13.8 billion years of light travel. The observable universe has a radius of approximately 46 billion light-years, even though the universe is only 13.8 billion years old. Beyond the event horizon, at distances greater than approximately 46 billion light-years, space is currently expanding away from us faster than light. Light emitted today from those regions will never reach us. They are permanently invisible, not because of the finite age of the universe, but because of the ongoing acceleration of the expansion by dark energy. This accelerating expansion, discovered in 1998 through observations of distant supernovae by the teams led by Saul Perlmutter, Brian Schmidt and Adam Rees, for which they received the 2011 Nobel Prize in Physics, adds a permanent component to the darkness of the night sky. Even if we waited an infinite amount of time, the sky would not brighten to the stellar surface level because dark energy is continuously expanding space, pushing more and more of the universe's stars beyond the event horizon, where their light can never reach us. The accelerating expansion means the night sky will actually become darker over cosmic time, not brighter. As the expansion continues and accelerates, galaxies beyond the local group gradually disappear behind the event horizon. Their light is stretched to undetectable wavelengths. Their contribution to the sky brightness drops to zero. The universe becomes progressively more isolated, each galaxy cluster eventually left alone in a dark, expanding void with no visible neighbours. In the extremely distant future, hundreds of billions of years from now, the night sky from any planet in what is then the merged Milky Way Andromeda galaxy will be darker than it is today. All other galaxies will have receded beyond the event horizon. The stars of the merged galaxy will be all that is visible against a black background. No other galaxies, no other stellar populations, no sign that a larger universe exists. The cosmic microwave background will have redshifted to wavelengths so long they are undetectable even in principle. This future darkness is a direct consequence of the same expansion that contributes to the darkness of the night sky today. The night sky is dark for the same reason that the cosmic future is dark. The universe is finite in age, finite in the volume from which we can receive light, and expanding in a way that continuously reduces the contribution of distant sources to the brightness of the sky. Let us now talk about the cosmic microwave background in more detail, because this ancient radiation is one of the most profound things in the universe, and it is directly related to Olbers' paradox in ways that are usually not explained. The early universe, before approximately 380,000 years after the Big Bang, was a hot, dense plasma. Protons, neutrons, electrons, and photons were all coupled together in a thermal equilibrium. Photons could not travel freely because they were constantly scattering off free electrons. The universe was opaque, like the inside of a star. At approximately 380,000 years after the Big Bang, the temperature dropped to approximately 3,000 Kelvin, cool enough for protons to capture electrons and form neutral hydrogen atoms. This transition, called recombination, happened rapidly throughout the universe. When electrons were captured by protons, the photons that had been scattering off them were suddenly free to travel. The universe became transparent. At that moment, the universe was filled with thermal radiation at 3,000 Kelvin, orange-hot radiation glowing uniformly from every direction. If you had been present and had eyes sensitive to the right wavelengths, the entire sky in every direction would have been glowing with the light of a 3,000 Kelvin surface, blazing orange in all directions simultaneously. That radiation is still present. It has been travelling freely through the expanding universe for 13.8 billion years. The expansion has stretched its wavelengths by a factor of approximately 1,100, from visible/near-infrared wavelengths appropriate for 3,000 Kelvin emission to microwave wavelengths appropriate for 2.725 Kelvin emission. Right now, the entire sky is glowing uniformly in microwave radiation from every direction simultaneously, as bright as a 2.725 Kelvin black body, which is extremely dim in the visible range, but real and measurable and uniform. If your eyes were sensitive to microwaves, you would see the entire sky glowing uniformly. No dark patches, no black background, every direction equally bright. The darkness of the night sky that you see with your eyes is partly because the ancient glow of the early universe has been shifted to wavelengths your eyes cannot detect. This is the most direct way in which the expansion of the universe explains the darkness of the night sky. The radiation that would make the sky bright, the thermal emission of the early hot universe, is still there. It is just invisible to human eyes because it has been redshifted out of the visible range. The CMB is extraordinarily uniform. Temperature variations across the sky of only about 1 part in 100,000. This uniformity reflects the extreme smoothness of the early universe. The tiny temperature variations that do exist, 1 part in 100,000, are the imprint of the quantum fluctuations that seeded the cosmic structure we see today, the galaxies, the clusters, the cosmic web. The CMB is a photograph of the universe at 380,000 years of age, and it shows us directly the state of the universe from which everything we see today evolved. Let us now talk about something that connects Olbers' paradox to information theory, because the darkness of the night sky is related to one of the deepest questions about the relationship between observers and the universe they observe. The observable universe, the sphere of space from which we have received light, contains approximately 10 to the 24 stars. This is a number large enough to make the sky bright if those stars were distributed in exactly the right way. But they are not. They are clumped in galaxies, and the galaxies are separated by voids, and most lines of sight from Earth miss all stars. But consider what the observable universe represents from an information theory perspective. Every photon that reaches your eye from a distant star carries information about that star: its temperature, its composition, its motion, its age. The light arriving from every direction simultaneously is an information stream from every part of the observable universe, reaching you continuously. You are at the center of a sphere of information. Every star, in every direction, within 46 billion light-years, is sending photons toward you right now. Most of them are too dim to detect without instruments, but they are arriving. The information is flowing inward to you from every direction. This is a remarkable position. Every observation you make, every photon you detect, is a message from the past. The photon that left a star 1 million light-years away carries information about the state of that star 1 million years ago. The photons of the CMB carry information about the state of the universe 13.8 billion years ago. You are surrounded by messages from the past, arriving continuously from every direction. The darkness of the night sky is partly a statement about the information density of the observable universe. If the sky were uniformly bright, if every line of sight terminated on a stellar surface, there would be no dark regions where we could look through to distant galaxies. The darkness between the stars is the transparency through which we observe the distant universe. It is the window through which the CMB arrives. A truly bright sky would obscure the very observations that allow us to understand cosmology. The darkness makes the richness of cosmological observation possible. The dark patches between stars are the windows through which we observe galaxy clusters, high redshift quasars, gravitational lensing, and the ancient light of the CMB. A Olbers bright sky, every direction as bright as a stellar surface, would be a sky from which no cosmological information could be extracted, because everything beyond the nearest star surface would be blocked. The darkness of the night sky is therefore not just a consequence of the universe's history. It is a prerequisite for our ability to understand the universe's history. Let us now talk about what the darkness of the night sky has meant historically, about how the question that became Olbers' paradox shaped scientific thinking about the nature of the universe long before modern cosmology existed. Johannes Kepler, in 1610, shortly after Galileo's telescopic observations revealed far more stars than are visible to the naked eye, recognized the problem clearly. If the universe is infinite and uniformly filled with stars, the night sky should be bright. Since it is not, Kepler concluded that the universe must be finite. It must have an edge, beyond which there are no stars. Kepler was partially right. His reasoning was correct, but his proposed solution was incomplete. The universe does have an effective observational edge, the edge of the observable universe, but this edge is not a physical wall beyond which nothing exists. It is the distance beyond which light has not had time to reach us. Edmund Halley, of Halley's Comet, also grappled with the paradox in 1720. He proposed that the distant stars must be so faint as to be invisible, which, as we discussed, fails as a solution because the number of stars increases with distance at the same rate their brightness decreases. Heinrich Olbers proposed his dust solution in 1823, wrong for the thermodynamic reasons we discussed. Edgar Allan Poe, yes, the author, proposed the correct solution in his 1848 prose poem Eureka. He wrote that the distance of the invisible background is so immense that light from the most remote stars has not yet reached us. Poe intuited the correct answer, the finite age of the universe causing a finite observable radius, before the physics to support it had been developed. He got there through aesthetic and philosophical reasoning rather than calculation. Lord Kelvin gave the first quantitative correct solution in 1901, calculating that the size of the observable universe, consistent with the finite age of the starlight reaching us, would produce a dark sky rather than a bright one. The modern understanding, incorporating both finite age and cosmic expansion, was developed in the 20th century as Hubble's expansion was discovered and general relativity's predictions for an expanding universe were confirmed. The history of Olbers' paradox tracks the history of cosmological understanding. Each proposed solution reflects the cosmological assumptions of its time. Kepler assumed a finite, bounded universe. Halley assumed brightness fades with distance. Olbers assumed steady-state absorption. Poe intuited finite look-back time. Kelvin calculated the finite age solution. The modern solution adds the expansion of the universe and the redshifting of distant radiation. The darkness of the night sky has been pointing toward the correct cosmology for centuries. The question, why is the sky dark, has the same answer as the question, what is the nature of the universe? They are the same question from different angles. Let us now talk about what you actually see when you look at the dark night sky, specifically about what the different components of the darkness are and what they tell us about the universe. When you look at the night sky, you see several distinct components. The bright stars, visible to the naked eye, approximately 5,000 to 10,000 in the entire sky, are individual stars, mostly within a few hundred to a few thousand light-years of Earth. They are nearby neighbours in the Milky Way. Their brightness varies enormously, from the brilliant Sirius at magnitude -1.46 to stars barely visible at magnitude 6, because of their different intrinsic luminosities and distances. The Milky Way band, visible from dark locations, is the combined light of billions of individual stars in the disk of our galaxy that cannot be resolved individually. They appear as a diffuse glow. The Milky Way contains roughly 200 to 400 billion stars, distributed in a disk approximately 100,000 light-years in diameter and about 1,000 light-years thick at our location. Most of the stars in this disk are unresolvable individually from Earth and contribute collectively to the diffuse glow. The dark regions within the Milky Way band, the dark lanes and patches, are not actual gaps in the stars, but are regions of dense interstellar dust that blocks the light from stars behind them. The Great Rift, the dark lane dividing the Milky Way, is a series of overlapping dust clouds in the spiral arm between us and the galactic center. The stars behind these dust clouds are real, but their light is absorbed and scattered by the dust. The faint fuzzy patches visible to the naked eye in very dark skies, the Andromeda Galaxy, the Triangulum Galaxy, the Magellanic Clouds from the southern hemisphere, are entire galaxies containing billions of stars each. Andromeda contains approximately 1 trillion stars at a distance of 2.537 million light-years. It appears as a small, fuzzy oval to the unaided eye, a patch smaller than the full moon, because its individual stars are unresolvable at this distance, and their light is blended into a diffuse glow. The truly dark sky, the black background between all these objects, is where Olbers' paradox operates. This black sky represents lines of sight that do not terminate on any stellar or galactic surface within the observable universe. It is transparency, a window through which we look into the depth of the universe without intercepting any luminous object. This black background is not truly empty of radiation. The cosmic microwave background fills it uniformly at 2.725 Kelvin, completely invisible to human eyes, but present everywhere simultaneously. The cosmic infrared background, the integrated light from all galaxies too faint and distant to be resolved individually, contributes a faint diffuse glow detectable by infrared telescopes. The cosmic X-ray background, the integrated emission from all active galactic nuclei and hot gas clusters, contributes at shorter wavelengths. The deepest images ever obtained, the Hubble Deep Field, the Hubble Ultra Deep Field, the Hubble Extreme Deep Field, and now the James Webb Space Telescope Deep Field images, reveal that what appears as black sky to the naked eye is actually filled with thousands of galaxies per square arc minute when observed with sufficient sensitivity. The James Webb Space Telescope's Deep Field images show galaxies at redshifts greater than 13, galaxies as they appeared when the universe was less than 400 million years old, packed into patches of sky that appear completely black to the naked eye. Every dark patch of sky contains thousands of galaxies if you look deeply enough. The blackness is not absence, it is depth. It is the transparency of the universe extending to the edge of the observable volume. This is one of the most striking facts revealed by deep imaging. The blackness of the night sky is not a void, it is a window. Every direction you look, the universe extends to the observable horizon, with galaxies all the way, most too faint and distant to resolve without powerful telescopes. The apparent darkness is not emptiness, but the invisibility of the incomprehensibly distant. Let us talk now about something that connects Olbers' paradox to the concept of entropy and the arrow of time, because the darkness of the night sky is related to the thermodynamic state of the universe in a way that is rarely discussed. In a universe in thermal equilibrium, a universe where everything is at the same temperature and no thermodynamic processes are occurring, the sky would be uniformly bright in all wavelengths. Everything would glow at the equilibrium temperature. No stars would be distinguishable from the background. No dark regions would exist. All directions would appear equally bright. The darkness of our night sky is evidence that the universe is not in thermal equilibrium. The sun is hotter than the sky background, 5,778 Kelvin versus 2.725 Kelvin. This temperature difference is what makes life on Earth possible. The difference between the high-quality energy arriving from the sun and the low-quality energy radiating away from Earth into the cold, dark sky drives all the thermodynamic processes of the biosphere. Photosynthesis, metabolism, weather, ocean circulation, all driven by the temperature difference between a hot star and a cold sky. The cold, dark sky is therefore not just a cosmological curiosity, it is a prerequisite for life. A sky as bright as a stellar surface, the Olbers bright sky, would be a sky in thermal equilibrium with stellar surfaces. The temperature of everything exposed to this sky would rise to stellar surface temperatures. No planets with liquid water, no life. The darkness of the sky is connected to the possibility of complex chemistry and biology. The darkness is also connected to the arrow of time. The second law of thermodynamics states that entropy increases. Systems evolve toward thermal equilibrium. The universe is currently far from thermal equilibrium. There are hot stars and cold space, dense planets and diffuse gas, organized galaxies and empty voids. This low entropy state is the legacy of the Big Bang, which produced an extremely low entropy initial condition. The darkness of the night sky reflects this low entropy. In a maximum entropy universe, the final thermal equilibrium state, the sky would be uniformly glowing at a uniform temperature everywhere. The fact that the sky is dark, that it has hot spots, stars, and cold regions, interstellar space, is evidence that the universe has not yet reached thermal equilibrium. It is evidence that the universe still has thermodynamic potential, still has the capacity to drive processes and power complexity. This thermodynamic potential, the difference between the hot sun and the cold, dark sky, is what makes your existence possible. You are a complex thermodynamic process driven by the temperature difference between a hot star and a cold universe. The darkness of the sky around the sun is the cold reservoir into which you dump entropy, allowing you to maintain your low entropy, organized state. The darkness of the night sky is not just an astronomical fact. It is the thermodynamic foundation of your existence. Let us talk about what modern observations have revealed about the components of the night sky darkness, specifically about the measurements that have been made of the total brightness of the sky, and what those measurements tell us about the integrated light from all sources in the universe. The total brightness of the night sky, measured across all wavelengths, has been carefully studied by astronomers using space-based instruments that can observe without the interference of Earth's atmosphere. The measurement is called the extragalactic background light, and it represents the integrated emission from all sources in the universe reaching us from outside the Milky Way. Measuring the extragalactic background light is technically difficult because it requires separating the faint diffuse background from foreground sources. The dominant foreground is the zodiacal light, sunlight scattered by dust in the plane of the solar system. This scattered sunlight produces a faint diffuse glow in the plane of the ecliptic that is significantly brighter than the extragalactic background. Subtracting the zodiacal light to reveal the much fainter extragalactic background is one of the primary technical challenges. The New Horizons spacecraft, which flew past Pluto in 2015 and is now in the outer solar system beyond the Kuiper belt, has been used to measure the optical extragalactic background light from a location far from the Sun, where the zodiacal dust contribution is dramatically reduced. The measurements from New Horizons found that the optical extragalactic background light is approximately twice the value that can be accounted for by counting all individually identified galaxies in deep field images. This factor of 2 discrepancy, the sky is twice as bright as the galaxies we can resolve can account for, has several possible explanations. There may be a significant population of very faint dwarf galaxies below the resolution threshold of current surveys that collectively contribute substantial light. There may be diffuse intergalactic light, starlight from stars stripped from their host galaxies during interactions and mergers, that drifts between galaxies without being associated with any galaxy. Or there may be other sources not yet identified. The James Webb Space Telescope's extraordinary sensitivity is providing new insight into this problem. JWST can detect galaxies at much higher redshifts and lower luminosities than previous telescopes, allowing a more complete census of the faint galaxy population that may account for the missing extragalactic background light. Early JWST results have identified more galaxies in deep field images than previous surveys counted, and the analysis of whether these newly detected faint galaxies account for the missing light is ongoing. The cosmic infrared background, the integrated light from all sources at infrared wavelengths, contains contributions from several epochs of cosmic history. The infrared background receives light from the first galaxies and quasars, whose light is redshifted into the infrared by the expansion of the universe. from dust-shrouded star-forming galaxies whose visible light is absorbed and reprocessed into infrared emission, and from the evolved stellar populations of mature galaxies emitting near-infrared light. The cosmic X-ray background, the integrated X-ray emission from all sources across the observable universe, is dominated by active galactic nuclei, accreting supermassive black holes, whose hard X-ray emission penetrates intervening gas and dust more effectively than softer radiation. Deep X-ray surveys by the Chandra X-ray Observatory and XMM Newton have resolved most of the cosmic X-ray background into individual sources, showing that it is the summed emission of hundreds of millions of accreting black holes spread across cosmic time. All of these backgrounds, optical, infrared, X-ray, microwave, together constitute the total radiation arriving at Earth from the sky. The CMB alone, the thermal relic radiation of the Big Bang, dominates the total by an enormous factor in terms of photon number and energy density. The optical and infrared backgrounds from galaxies are tiny in comparison. The total energy density of radiation in the universe is dominated by the CMB. The visible and near-infrared starlight from all galaxies contributes roughly half the energy density of the CMB in photons. This means that most of the photons in the universe are CMB photons, ancient relics of the hot, early universe, and that the collective light of all stars and galaxies throughout cosmic history is comparable in total energy to the stretched glow of the Big Bang's afterglow. This is Olbers' paradox in quantitative form. The total starlight is not infinite. It is finite and comparable in energy density to the CMB. The sky is dark because this finite amount of starlight, while enormous in absolute terms, is distributed across the entire sky and the entire observable volume in a way that makes any given direction of the sky very faint in starlight contribution. Let us now talk about what the expanding universe means for the fate of the night sky's darkness, following the timeline of cosmic history forward to see how the night sky changes over time. In the very early universe, before the first stars formed, the sky was dark in the sense of having no stars, but was not dark overall. The universe was filled with hot plasma emitting thermal radiation. The sky was uniformly bright with the orange glow of plasma at thousands of Kelvin. After recombination, the universe became transparent and the CMB radiation propagated freely. But there were no stars, no galaxies, only diffuse hydrogen and helium gas cooling as the universe expanded. This period, from recombination at approximately 380,000 years to the formation of the first stars at approximately 100 to 200 million years, is called the Cosmic Dark Ages. Not dark in the sense of the sky being black, the CMB was still bright, but dark in the sense of no stars, no galaxies, no visible light sources. The universe was transparent, but empty of luminous objects. When the first stars formed, massive, hot, short-lived population 3 stars burning hydrogen at extreme rates, the cosmic dark ages ended. These stars ionized the surrounding hydrogen gas in growing bubbles of ionized space, a process called reionization that completed by approximately 1 billion years after the Big Bang, when essentially all the intergalactic hydrogen was reionized. During the epoch of reionization, the night sky would have been different from today. More active, young, hot, massive stars exploding as supernovae at high rates, active galactic nuclei in early massive galaxies blazing with accretion power, the universe denser and more violent than the comparatively quiescent universe of today. Today, we live in a relatively mature universe. The peak of star formation, the cosmic noon, was approximately 10 billion years ago, when star formation rates were roughly 10 times higher than today. The peak of quasar activity was approximately 10 to 12 billion years ago. Today, the universe is past its most active phase and settling into a comparatively quiet middle age. The night sky today reflects this history. We see not just the nearby stellar population, but through deep imaging we can see galaxies at every epoch, from the distant past to the present, a time-lapse record of cosmic evolution, visible simultaneously in different directions at different distances. As the universe continues to evolve, the night sky will change. Over the next several billion years, the sun will brighten and eventually expand into a red giant, engulfing the inner planets. The Milky Way and Andromeda will merge in approximately 4.5 billion years. The merger will trigger a burst of new star formation that will temporarily brighten the stellar population of the merged galaxy. The resulting galaxy, sometimes called Milkomeda or Milkdromeda, will eventually settle into a large elliptical galaxy with an aging stellar population. Over the next tens to hundreds of billions of years, galaxies beyond the local group will gradually recede behind the cosmological event horizon as dark energy continues to drive accelerating expansion. Their light, already faint, will be increasingly redshifted and eventually redshifted to undetectable wavelengths. The night sky will become progressively darker as the observable universe shrinks in accessible content, even though its physical size continues to expand. In the very distant future, after hundreds of billions to trillions of years, the night sky from any planet in the remnant of the Milky Way Andromeda galaxy will be dramatically different from today. No other galaxies will be visible. The CMB will have been redshifted to wavelengths so long, radio wavelengths and longer, that no conceivable detector could register it. The sky will appear completely dark, except for the stars of the local galaxy, and as those stars progressively exhaust their fuel and die, the sky will become darker still. Eventually, the last stars will fade. The night sky will be truly dark, black in every direction. No stars, no galaxies, no CMB. The darkness of maximum entropy. The darkness of the heat death. The only sources of faint radiation will be the evaporating black holes emitting Hawking radiation, an extraordinarily faint glow from objects cooling over timescales of 10 to the power of 100 years. The darkness of the night sky today, beautiful, profound, rich with galaxies and history, is a temporary condition. The universe will become darker and darker, and eventually the darkness will be complete. Let us now talk about what the specific spectrum of night sky darkness reveals, about the colour of the universe, and what it tells us about the integrated stellar population across cosmic history. The universe has a colour. Not the darkness of the night sky in visible light, but the colour of the total integrated light from all stars and galaxies throughout the observable universe, averaged together. This colour was calculated in 2002 by Carl Glazebrook and Ivan Baldry from spectroscopic data from the 2DF Galaxy Redshift Survey. They averaged the colours of more than 200,000 galaxies, weighted by their contributions to the total luminosity. The result was a slightly beige white, a colour they initially named Cosmic Latte, after the coffee drink. The specific colour, in terms of the Commission Internationale de l'Éclairage colour space, is approximately a warm cream white, corresponding roughly to the colour of a 4000 Kelvin blackbody, slightly bluer than the warm white of an incandescent light bulb. This colour reflects the integrated stellar population of the universe. Young, hot blue stars contribute blue light. Old, cool red stars contribute red light. The mix of young and old stellar populations across all galaxies produces the intermediate warm white average. The fact that the colour is slightly warm, slightly red compared to pure white, reflects that the universe today is past the peak of star formation and contains a substantial population of old red stars. In the early universe, at cosmic noon when star formation was at its peak, the integrated colour of the universe would have been bluer, reflecting the dominance of young, hot, massive stars. As the universe ages and the stellar population becomes dominated by old, cool stars, the integrated colour will redden further. In the far future, when only cool, red dwarf stars remain burning, the colour of the universe will be distinctly red. The last light in a darkening universe will be red. The darkness of the night sky visible to human eyes is not the total radiation environment. It is the radiation at optical wavelengths specifically. We are visually sensitive to wavelengths between approximately 380 nanometers, violet, and 700 nanometers, red. The universe emits radiation across a much wider spectrum, from gamma rays to radio waves, and our experience of the night sky is limited to the narrow window our eyes can perceive. A radio telescope looking at the sky sees it uniformly bright with CMB radiation, the entire sky glowing at 2.725 Kelvin. An infrared telescope sees the faint integrated starlight of all galaxies plus the zodiacal dust emission. An X-ray telescope sees the active galactic nuclei and hot galaxy cluster gas contributing the cosmic X-ray background. At gamma-ray frequencies, the sky shows the most energetic sources: blazars, gamma-ray bursts, and neutron star mergers. Our experience of a dark night sky is an artifact of our specific visual sensitivity range. We happen to be sensitive to wavelengths where the sky is particularly dark, where stars are bright points against a dark background. If we were sensitive to radio wavelengths, we would experience the sky as uniformly glowing in every direction. If we were sensitive to extreme ultraviolet, we would see the ionized gas of galaxy clusters glowing throughout the sky. The darkness of the night sky is therefore partly a statement about human visual biology, about the specific narrow window of the electromagnetic spectrum to which our eyes are sensitive. Evolution tuned our vision to the optical window of Earth's atmosphere, the range of wavelengths to which the atmosphere is most transparent and which contains the peak emission of our Sun. In that window, the sky happens to be mostly dark. Stars are bright against a black background. This tuning is not coincidental. It reflects the fundamental relationship between life on Earth and the solar radiation that drives it. Our eyes see best at the wavelengths where the Sun is brightest, which is also the wavelength range where the night sky is darkest, because the CMB radiation has been redshifted far out of this range, and the total starlight from all galaxies is faint compared to nearby stars. Let us talk about what the darkness of the night sky tells us about the concept of infinity, because Olbers' paradox was originally formulated as an argument against an infinite, eternal universe, and the resolution of the paradox illuminates what kinds of infinities are and are not consistent with observation. An infinite universe does not necessarily produce a bright sky. The resolution of the paradox shows this clearly. Even if the universe is spatially infinite, even if it extends without bound in all directions, the night sky can be dark if the universe has a finite age. The light from infinitely distant stars has not had time to reach us. Infinity of space does not imply infinity of observable content. This is a specific and important lesson about the relationship between mathematical infinity and physical observability. A universe can be spatially infinite and yet have a finite observable volume. The observable universe, the sphere of space from which we have received light, is finite, even if the total universe is infinite. Infinity of the total does not imply infinity of what can be observed from any given point. An eternal universe with infinite past, a universe that has always existed without a beginning, would produce a bright sky, because light from infinitely distant sources would have had infinite time to reach us. This is the original Olbers observation. An infinite, eternal universe implies a bright sky. Since the sky is dark, either the universe is not infinite, or it is not eternal. Modern cosmology tells us the universe is finite in age. It has a beginning 13.8 billion years ago, which resolves the paradox regardless of whether the universe is spatially finite or infinite. The expansion of the universe adds another way that infinity is tamed. Even for an infinite spatial universe, the expansion ensures that sources beyond the cosmological event horizon can never send light to us, regardless of how long we wait. An infinitely large, expanding universe has a finite observable volume at any given time, and dark energy ensures this finite observable volume will never grow to encompass more than it contains today. The accessible information in the universe is bounded, even if the universe itself is unbounded. This is profound. The universe may be infinite, may contain infinitely many stars, infinitely many galaxies, infinitely many planets, infinitely many copies of every possible configuration of matter, including exact copies of Earth and you. But you can only ever observe a finite portion of it. The darkness of the night sky is a visual reminder of this fundamental bound on observability. The black sky between the stars is the boundary of the accessible universe, not a physical wall, but an informational horizon beyond which no signal can reach us in any finite time. The stars you can see are neighbours. The galaxies visible through telescopes are the accessible community. Everything beyond the observable horizon is present but inaccessible. Real in whatever sense the universe is real, but not observable in any way that has practical consequences for us. Let us talk about a specific observational consequence of the expansion that connects directly to Olbers' paradox. The concept of look-back time and what it means to see the universe as it was rather than as it is. When you look at a star 1 light-year away, you see it as it was 1 year ago. The light entering your eye left that star 1 year ago and has been travelling toward you ever since. You are not seeing the star as it is now, but as it was. This is not a philosophical subtlety, it is a physical fact with real consequences. When you look at a galaxy 1 billion light-years away, you see it as it was 1 billion years ago, when the universe was younger, when stars were more actively forming, when supermassive black holes were more actively accreting. You are observing the past directly. The night sky is a time machine. Different distances correspond to different epochs of cosmic history. This look-back time is why Hubble Deep Field images are not just images of distant galaxies, they are images of the early universe. The faintest, most distant galaxies in those images existed 13 billion years ago, when the universe was only a few 100 million years old. They may no longer exist in the same form. They may have merged with other galaxies, been disrupted, or evolved into very different structures over the 13 billion years since the light left them. The universe we observe at any moment is a composite of different epochs, nearby stars as they are essentially now, nearby galaxies as they were millions of years ago, distant galaxies as they were billions of years ago, the CMB as the universe was 13.8 billion years ago. The entire history of the universe is visible simultaneously, different layers of time visible at different distances. This temporal depth is unique to observations of the universe and has no analogue in everyday experience. Looking at a building, you see it as it is now. The light travel time is nanoseconds, completely negligible. Looking at the moon, you see it as it was 1.3 seconds ago. Looking at the sun, you see it as it was 8.3 minutes ago. But looking at distant galaxies and the CMB, you see epochs billions of years in the past. The further you look, the further back in time you see. Olbers' paradox operates across this temporal depth. The darkness of the sky depends not just on how many stars exist now, but on the integrated emission from stars across all of cosmic history, the stellar emission that has had time to reach us from the entire observable volume across the entire age of the universe. This integrated emission is finite, bounded by the age of the universe and the expansion, and produces the specific level of background brightness that we observe. Let us now talk about what gravitational lensing adds to the story of the night sky's darkness, because gravity bends light, and this bending has implications for how light from distant sources reaches us. Massive objects, galaxies, galaxy clusters, dark matter concentrations, bend light through the curvature of space-time described by general relativity. A galaxy cluster between us and a more distant galaxy acts as a gravitational lens, bending the light from the background galaxy and potentially focusing it toward us. This can dramatically amplify the apparent brightness of the background source. Gravitational lensing means that the night sky is not simply a geometric projection of sources onto a two-dimensional background. The distribution of brightness is distorted by the gravitational field of all the mass between us and each source. Some background sources are brightened by lensing, appearing brighter than they would be without the intervening mass. Some are dimmed by being on the wrong side of the lens to receive focused light. The most dramatic manifestation of gravitational lensing is in galaxy cluster images, where background galaxies are stretched into arcs and rings by the powerful gravity of the cluster. These lensed images can be dozens of times brighter than the unlensed source, allowing the observation of very distant, faint galaxies that would otherwise be undetectable. Gravitational lensing contributes to the extragalactic background light. Some of the diffuse background brightness comes from galaxies that have been weakly lensed by the cosmic large-scale structure, slightly brightening them and spreading their light over slightly larger areas of sky. The total effect on the background brightness is modest but real. More importantly for cosmology, gravitational lensing is one of the primary tools for mapping the distribution of dark matter, which itself contributes to the gravitational lensing that shapes the light reaching us. The night sky, as seen through a powerful telescope, is not a simple projection. It is a gravitationally distorted map of sources through an inhomogeneous matter distribution. Let us now talk about something that takes the question in an unexpected direction, about what Olbers' paradox implies for civilizations in different cosmological environments. Consider a civilization living in a globular cluster, a dense spherical cluster of approximately 100,000 stars packed into a region about 100 light-years across. The stellar density in the core of a globular cluster is hundreds to thousands of times higher than in our galactic neighborhood. Stars are separated by fractions of a light-year rather than several light-years. For such a civilization, the night sky would look very different. Instead of a few thousand stars visible to the naked eye, with dark sky between them, there would be hundreds of thousands of stars visible, many so close and bright that the night sky would be significantly more illuminated. The Milky Way background would be brighter. The overall sky brightness would be higher. In the densest cores of the densest globular clusters, where stars are separated by distances measured in light weeks rather than light years, the night sky would be dramatically bright. Not Olbers bright, not as bright as a stellar surface, because the angular coverage of individual stars is still small even at close distances, but the night sky would be visually spectacular, thousands of bright stars creating a much more luminous background than we experience. The consequences for life in such an environment are significant. The higher background stellar density means higher rates of stellar flybys that can perturb planetary orbits and disrupt the stability of planetary systems. The higher stellar density also means more exposure to radiation events, nearby supernovae, stellar flares from close neighbors. Globular cluster cores may be hostile to long-term planetary habitability for reasons related to their stellar density, which is also the reason their night sky is different. Alternatively, consider a civilization in one of the massive cosmic voids, the enormous empty regions between the filaments of the cosmic web. A civilization in such a void would be hundreds of millions of light-years from the nearest cluster of galaxies. Their night sky would be emptier even than ours, fewer nearby galaxies, a sky even darker than Earth's. Their experience of isolation would be profound, their galaxy alone in an enormous empty expanse. The specific darkness of the night sky experienced by any civilization depends on its location in the large-scale structure, in a filament, in a cluster, in a void, and on the epoch of cosmic time. Our particular experience of the night sky is one point in a vast distribution of possible sky darknesses, depending on where and when in the universe you observe. Let us now talk about the specific mathematics of why the resolution of Olbers' paradox is satisfying, about why the numbers work out to produce a sky that is dark enough to be compatible with life, but not completely empty of radiation. The total energy density of starlight integrated over the entire observable universe and the entire age of the universe, the optical extragalactic background light, is measured to be approximately 54 nanoelectron volts per cubic centimetre. This is an extraordinarily small energy density, roughly 10,000 times smaller than the energy density of the CMB. If this starlight were uniformly redistributed across the entire sky, it would produce a sky brightness of approximately 30 to 50 photons per second per square centimetre per steradian in the optical band. This is roughly 10 to 100 times fainter than the darkest observable night sky on Earth, which is also affected by airglow, atmospheric emission, zodiacal light, and the integrated light of unresolved stars in the Milky Way. The total night sky brightness on the darkest nights on Earth, measured far from artificial lights at high altitude away from the Milky Way, corresponds to approximately 22 magnitudes per square arc-second, one of the standard measures of sky brightness in astronomy. Of this, The extragalactic background contributes approximately 24 to 25 magnitudes per square arc-second, a factor of roughly 10 fainter than the total sky brightness. The Milky Way stars, zodiacal light and air glow, dominate the observable sky brightness. The contribution of all galaxies beyond the Milky Way to the night sky brightness is therefore very small. Not zero, but small. It is the correct small number, the number produced by a universe of finite age and expanding space with a specific history of star formation. Had the universe been 10 times older, or had the star formation rate been 10 times higher throughout its history, the extragalactic background would be 10 times brighter, but still not Olbers bright. The sky would need to be approximately 10 to the 13th to 10 to the 15th times brighter than the total starlight background to achieve the brightness of a stellar surface. The resolution of Olbers' paradox requires only a factor of roughly 10 to the 14th below the stellar surface brightness, and the combination of finite age, finite observable volume, and cosmological redshift provides this suppression comfortably. The numbers work because they had to, not because they were designed, but because a universe where the sky was Olbers bright would be a universe where life was impossible, and we observe a universe where life is possible. The dark sky is a selection effect as well as a physical fact. We exist in conditions where we can exist, and dark skies are part of those conditions. Let us now talk about one more aspect of night sky darkness that is rarely discussed: the specific role of the intergalactic medium in the darkness of the sky and how it changes across cosmic time. The intergalactic medium, the gas filling the space between galaxies, is not completely empty or completely transparent. It contains diffuse hydrogen and helium in various ionization states, a cosmic web of gas tracing the dark matter filaments, and pockets of denser gas associated with galaxy halos. This diffuse gas absorbs certain wavelengths of light, particularly the ultraviolet radiation below the hydrogen-Lyman limit at 91.2 nanometers. For distant sources at high redshift, this ultraviolet absorption is dramatically important. The Lyman break, the sharp cutoff in a galaxy's spectrum at the Lyman limit, is shifted to longer wavelengths by the cosmological redshift. For a galaxy at redshift 3, the Lyman limit is shifted to approximately 365 nanometers, in the near ultraviolet just outside the visible range. For galaxies at redshift 5 or above, the Lyman limit is shifted into the blue and green visible range, meaning that all wavelengths shorter than this limit are absorbed by the intergalactic hydrogen, making the galaxy appear as if it has no emission shortward of the shifted Lyman limit. For very high redshift galaxies, at redshift 6 and above, the intergalactic medium absorption is severe enough to absorb essentially all radiation shortward of the Lyman limit, which is shifted to red and near-infrared wavelengths. This is called Gunn-Peterson absorption, and its sudden appearance in the spectra of high redshift quasars at redshift approximately 6 indicates that the intergalactic hydrogen was still largely neutral at those epochs. The universe had not yet fully reionized. The intergalactic medium therefore acts as a filter that absorbs high-energy photons from distant sources, making the sky effectively darker at ultraviolet wavelengths than it would be if the medium were transparent. This absorption reduces the contribution of distant high redshift sources to the ultraviolet and visible sky brightness. Conversely, the absorption of hard ultraviolet radiation by the intergalactic medium, and the subsequent heating and reionization of the medium by this absorbed radiation, is one of the primary processes shaping the large-scale structure of the universe. The ultraviolet radiation from the first stars and quasars that re-ionized the universe was precisely the radiation that the intergalactic medium absorbed to drive re-ionization. The darkness of the sky at ultraviolet wavelengths is partly the consequence of this absorbed radiation. Light that would have contributed to the background has instead been absorbed and used to ionize the intergalactic gas. This connection between the ultraviolet darkness of the high redshift sky and the re-ionization history of the universe is one of the threads connecting Olbers' paradox to the history of cosmic structure formation. The specific transparency of the universe at different wavelengths and different epochs reflects the physics of how matter and radiation have interacted across 13.8 billion years of cosmic evolution. Let us now bring all of these threads together and see the full picture of why space is dark despite containing a septillion stars. The night sky is dark for several reasons operating simultaneously. None alone is sufficient. Together, they produce the specific darkness we observe. The universe has a finite age of 13.8 billion years. Light from objects more than approximately 46 billion light years away, accounting for expansion, has not had time to reach us. This creates a finite observable volume containing a finite number of stars and galaxies. The density of stars in this finite volume is not sufficient for every line of sight to terminate on a stellar surface. The universe is expanding. Light from distant sources is redshifted, stretched to longer wavelengths and lower energies by the expansion of the space through which it travels. Photons from very distant galaxies arrive at Earth with a fraction of the energy they had when they were emitted. The contribution of distant sources to sky brightness is dramatically reduced by this energy loss. The expansion is accelerating. Dark energy drives an accelerating expansion that will eventually move all galaxies beyond the local group behind the cosmological event horizon, permanently cutting off their light. The effective observable volume is not growing to eventually encompass more sources. It is bounded by an event horizon that the accelerating expansion maintains. The universe has a specific, finite history of star formation. Stars have only been burning for approximately 13.6 billion years. They did not always exist. The total energy in starlight is bounded by the finite time over which stars have been operating and the finite fraction of the universe's mass that has been converted to stellar fuel. This finite total energy is distributed across the entire sky and is insufficient to produce a bright background. The most ancient radiation, the thermal glow of the hot early universe, has been redshifted by a factor of 1,100 out of the visible range into microwaves. The radiation that would most directly produce an Olbers bright sky, the thermal emission of the early hot plasma, is completely invisible to human eyes. It is present, but invisible, filling the sky at microwave frequencies in every direction simultaneously. All 5 of these reasons, finite age, expansion, accelerating expansion, finite star formation history, CMB redshift, work together to produce a sky that is dark in the visible range and in thermal equilibrium with a temperature of 2.725 Kelvin rather than thousands of Kelvin. This darkness is not a gap in our understanding or an anomaly requiring explanation. It is precisely what a universe with these properties should produce. The explanation is complete. The calculation agrees with observation. Olbers' paradox is resolved. But the resolution carries implications that go far beyond the immediate question. It tells us the universe has a beginning. It tells us the universe is expanding. It tells us the expansion is accelerating. It tells us the universe has a specific, finite history of structure formation. It tells us that what we can observe is bounded by a fundamental horizon. It tells us that the darkness of the sky is connected to the thermodynamic conditions that make complex chemistry and life possible. The darkness between the stars is not emptiness, it is depth. The depth of the observable universe extending to the cosmological horizon. It is history, the look-back time to every epoch of cosmic evolution visible simultaneously at different distances. It is the CMB, the ancient light of the hot early universe, invisible to our eyes but filling every dark direction. It is the intergalactic medium, the diffuse gas tracing the cosmic web between galaxies. It is the event horizon of the accelerating expansion, the boundary beyond which the universe is real but inaccessible. Every dark patch of night sky is a window into the observable universe's depth. Every dark direction contains galaxies, thousands of them per square degree visible in deep images. Every dark direction is bathed in the CMB. Every dark direction looks back in time to the earliest observable epoch of cosmic history. The darkness is not nothing. It is everything the observable universe is, compressed into a faint, nearly invisible background below the threshold of unaided human perception. Stars are everywhere. Space is dark because the universe is young enough, expanding enough, finite enough in its history of star formation, that the light from all those stars has not yet had time, and will not have time, to fill the sky. The darkness is the gap between what the universe contains and what it has had time and energy to illuminate. Let us talk about what the darkness of the night sky means for one of the most active areas of current astronomy: the search for the first light in the universe, the epoch when the darkness of the cosmic dark ages was first broken by the formation of the first stars. Between recombination at 380,000 years after the Big Bang and the formation of the first stars at perhaps 100 to 200 million years after the Big Bang, the universe was dark in a literal and complete sense. The CMB radiation was present, diffuse, cooling, filling all of space, but no luminous objects existed. No stars, no galaxies, no quasars. The universe consisted of hydrogen and helium gas, slowly cooling and condensing under gravity in the dark. This is called the cosmic dark ages because no optical radiation was being produced anywhere in the universe. If you had been present with human eyes, you would have seen nothing in any direction. The CMB had already cooled to wavelengths far below visible light, and no stars existed yet. Total darkness in the human visual sense. The first stars, population 3 stars, formed from pure primordial hydrogen and helium with no heavier elements, were massive and hot and short-lived. They burned bright and blue and violently for only a few million years before exploding as supernovae. Their formation ended the cosmic dark ages and began the epoch of reionization, the period during which their ultraviolet radiation ionized the surrounding neutral hydrogen, gradually ionizing all the intergalactic medium over the course of hundreds of millions of years. The specific properties of these first stars Their masses, temperatures, lifetimes, the radiation they produced are among the most sought-after unknowns in modern astronomy. We have never directly observed a population 3 star. They formed and died before any of the galaxies we can currently observe in detail were assembled. Their signature should be encoded in the properties of the oldest metal-poor stars in nearby galaxies. Second-generation stars formed from gas enriched by population 3 supernovae, and in the specific reionization history of the intergalactic medium. The James Webb Space Telescope is specifically designed to probe the epoch of reionization and to search for the signatures of the first galaxies. It can observe rest-frame optical and ultraviolet emission redshifted into the near-infrared, allowing it to detect and characterize galaxies at redshifts above 10, when the universe was less than 500 million years old. Early JWST observations have identified galaxy candidates at redshifts as high as 16, corresponding to when the universe was only about 250 million years old. Whether any of these high redshift galaxies contain or are associated with population 3 stars is being actively investigated. The specific spectral signatures of population 3 stars, particularly the helium emission lines produced by ionized helium, which requires extremely hot stars, are being searched for in the most distant and most metal-poor galaxy candidates. A definitive detection of population 3 star signatures would be one of the most significant discoveries in the history of astronomy. The transition from the cosmic dark ages to the first light is directly relevant to Olbers' paradox because it defines the epoch when the universe first began contributing to the extragalactic background light. Every photon of optical radiation in the extragalactic background was produced after this transition, during the 13.6 billion years of stellar activity since the first stars formed. The darkness of the night sky is partly a record of this finite history of stellar emission. The 21 centimeter radio signal, emission from neutral hydrogen at its characteristic spin-flip frequency, is the most promising probe of the cosmic dark ages and the epoch of reionization. Before and during reionization, the intergalactic neutral hydrogen emitted and absorbed 21 centimeter radiation in a pattern that depended on the density, temperature, and ionization state of the gas. Detecting this signal, redshifted from 1420 MHz to much lower frequencies by the cosmic expansion, would directly map the distribution of neutral hydrogen during reionization and provide information about when and how the first stars and galaxies lit up. This detection is extraordinarily difficult. The redshifted 21 centimeter signal from the epoch of reionization falls in the radio frequency range of 50 to 200 MHz, a range plagued by terrestrial radio interference from FM radio stations, aircraft navigation beacons, and other sources. Separating the faint cosmological signal from this foreground is a technical challenge of the highest difficulty. Several radio telescopes are pursuing this goal: the Hydrogen Epoch of Reionization Array in South Africa, the Murchison Wide Field Array in Australia, the Low Frequency Array in Europe. The most ambitious proposal is a radio telescope on the far side of the Moon, where the Moon itself shields the instruments from all terrestrial radio interference. A far-side lunar radio telescope is proposed in various concepts and would be capable of detecting the 21 centimeter signal from the epoch of reionization with unprecedented sensitivity. The specific darkness of the night sky at low radio frequencies, below approximately 30 MHz, is itself a consequence of the opacity of Earth's ionosphere. The ionosphere reflects radio waves below this frequency back to Earth, which is why AM radio can propagate around the Earth by bouncing between the ionosphere and the ground. This ionospheric opacity makes the universe below 30 MHz invisible from the ground. The universe at these very low frequencies is one of the last unexplored frontiers of observational astronomy. The only way to observe it is from space, above the ionosphere, or from the far side of the Moon. The specific darkness of the sky to Earth-based observers at these wavelengths is an artifact of the Earth's ionosphere rather than of any astrophysical effect. Remove the ionosphere, go to space or the far side of the Moon, and the sky opens up at these wavelengths to reveal the epoch of reionization and possibly even earlier epochs. Let us now talk about what advanced civilizations might infer about the universe from the darkness of their night sky. A thought experiment that illuminates what the darkness tells us and what alternative darkness patterns might indicate. A civilization in a very old universe, a universe much older than ours, would see a darker night sky because more of their observable universe's stars would have already burned out. The CMB would be cooler, stretched to even longer wavelengths by more years of expansion. The galaxies beyond their local group might have already receded behind the cosmological event horizon. Their night sky would be dominated by the slowly fading stellar remnants of their own galaxy, white dwarfs cooling to black dwarfs, neutron stars slowing down, black holes evaporating infinitely slowly through Hawking radiation. Such a civilization, if it existed, would have a much harder time deducing the cosmological history of their universe. The evidence for the Big Bang, the CMB, the Hubble expansion, the high redshift galaxies, would be largely inaccessible to them. They might conclude from their dark and apparently static sky that the universe has always been as it is, an island galaxy in eternal darkness, when in fact their universe has a Big Bang origin and a long history of cosmic evolution that the evidence no longer reveals. A civilization in a young universe, a universe much younger than ours, would see a very different night sky. The CMB would be warmer, less redshifted, brighter at shorter wavelengths, possibly contributing a perceptible glow. The universe would be denser, galaxies closer together, filaments more compact, voids less empty. The night sky between stars would be brighter, more background galaxies closer and brighter, the CMB contributing more to the optical background. Star formation rates would be higher, more active galaxies, more quasars, a more energetic and active universe. Their Olbers paradox would be less severe. The sky would be brighter in their epoch than in ours, closer to the Olbers bright limit, but still dark enough to see stars as individual objects against a background. This thought experiment illustrates that the specific darkness of the night sky is a function of cosmic epoch as well as cosmological parameters. We happen to live in an epoch and location where the sky is particularly informative, dark enough to see individual stars and galaxies, but not so dark that all distant sources are invisible. We live in the era of galaxies, the epoch when the universe is richly structured and actively star-forming, which is precisely when Olbers' paradox produces the most interesting answer. Let us talk about what the darkness of space means specifically in the context of human space travel, because astronauts experience the darkness of space directly, and their reports of that experience illuminate what the darkness actually is. From the surface of the Earth, the night sky is dark but complicated. There is an atmosphere that scatters sunlight, producing twilight and sky glow, a moon that illuminates the landscape on clear nights, and from inhabited areas, the artificial lights of human civilization, creating light pollution that washes out the fainter stars and galaxies. The darkest skies on Earth, at high-altitude observatories far from human settlements, still have the airglow of the upper atmosphere adding to the background. From space, outside the atmosphere, the experience of the sky is different. The Earth shines brilliantly, the blue planet in black space, reflecting sunlight with extraordinary brightness against the absolute dark background. The Sun is a blazing disk of white light with no atmospheric scattering to soften it. Looking directly at the Sun from space without protection would be immediately damaging to vision. The stars are points of light without the atmospheric twinkling that makes them shimmer from the ground. Steadier, sharper, more numerous, because without the atmosphere's absorption, the fainter stars become visible. Astronauts on the International Space Station experience the darkness of space 16 times per day as their orbit takes them alternately into sunlight and into Earth's shadow. In Earth's shadow, with the interior lights of the station dimmed, the sky is extraordinarily dark. The Milky Way is visibly bright. Stars down to the 4th or 5th magnitude are easily visible even in the station's vicinity, and the Earth below shines with city lights against the dark ocean. The moon landings provided the most direct human experience of the darkness relevant to Olbers' paradox. From the lunar surface in daylight, the sky is black. Not dark blue as on Earth, but absolutely black, because the moon has no atmosphere to scatter the sunlight. The sun blazes in the black sky as a white disk, brighter than anything on Earth. The stars are not visible in the daylit sky from the lunar surface, not because they are absent, but because the same reason they are not visible in the daylit sky on Earth. The bright surface below scatters enough light that the much fainter stars are lost in the glare. In the lunar night, the 2-week period of darkness, the sky from the lunar surface would display the full darkness of space, with no atmosphere to add airglow and no scattered light from nearby sources. The Milky Way would blaze across the sky. Individual stars would be completely steady, no twinkling. The Earth would appear as a large bright disk, roughly 4 times the angular diameter of the Moon as seen from Earth, going through phases as the Sun illuminates different portions of its face. This specific experience, black sky in daylight from the Moon, blazing stars in lunar night, directly illustrates the resolution of Olbers' paradox. The sky is dark in the daytime not because there are no stars, but because the bright nearby source, the Sun, overwhelms the faint background. In the night, the background becomes visible: stars, Milky Way, galaxies, but still against a dark background because the total starlight is insufficient to produce a bright sky. The darkness of space that astronauts experience is precisely the darkness that Olbers' paradox requires explanation for. It is the darkness of a finite age expanding universe with a specific history of star formation. It is not obvious. It required 250 years of scientific thinking from Kepler to Kelvin to explain. Let us talk now about the specific role that the darkness of the night sky plays in our ability to do astronomy, in our ability to discover and study the contents of the universe at all. If the night sky were as bright as a stellar surface, the Olbers bright limit, astronomy as we know it would be impossible. Every telescope pointed at any direction of the sky would see only the uniform blazing brightness of the stellar surface filling the entire field of view. There would be no stars to resolve as individual points because every direction would be equally bright. There would be no galaxies to observe because the background would overwhelm any distant source. There would be no CMB to detect because it would be swamped by the optical radiation filling every direction. The entire science of astronomy depends on the sky being dark. The ability to see individual stars as points of light against a dark background. The ability to observe individual galaxies at different distances and epochs. The ability to detect the faint diffuse CMB against an effectively dark background at microwave frequencies. The ability to measure the redshifts of distant sources and thereby determine the expansion history of the universe. All of this is possible only because the sky is dark, because Olbers' paradox is resolved in the specific way it is resolved. The darkness of the sky is what allows us to know the history of the universe. The transparency of the universe at optical wavelengths, its darkness between stars and galaxies, is what allows light from distant epochs to reach us and carry the information needed to reconstruct cosmological history. A bright, opaque universe would be a universe whose history was inaccessible to observation. The specific parameters that resolve Olbers' paradox, finite age, expanding space, finite star formation history, are also the parameters that make the universe knowable. A universe with the same number of stars, but arranged differently, uniformly distributed in an infinite, eternal, non-expanding universe, would not only have a bright sky, but would be a universe whose cosmological history was permanently inaccessible to any observer within it. The darkness of the sky is the same physical fact as the observability of cosmic history. This is a deep connection. The universe can be understood precisely because it has the properties that resolve Olbers' paradox. The darkness that allows us to see stars is the same darkness that allows us to see galaxies, is the same darkness that allows us to see the CMB, is the same darkness that reveals the Big Bang and the expansion and the age of the universe. Olbers' paradox and observational cosmology are not separate questions. They are the same question from different angles. Let us talk about what the darkness of the night sky has meant culturally and philosophically, about how the specific experience of a dark sky with bright stars against black has shaped human thinking and human feelings about the universe across cultures and throughout history. The dark night sky is one of the oldest human experiences. Before artificial light, before cities, before agriculture, before recorded history, every human being lived under a dark sky every clear night. The stars were visible in their full splendor, not the few dozen visible in modern light-polluted cities, but thousands, with the Milky Way blazing across the sky as a bright band of light. The planets moved among the fixed stars. The moon went through its phases. Meteor showers streaked overhead. The aurora decorated northern and southern skies. This experience shaped mythology, religion, navigation, agriculture, and the first stirrings of science. The specific patterns of stars, constellations, were given names and stories in every culture. The regularities of celestial motion, the predictable return of seasons, the cycles of the moon, the wandering of planets, were the first objects of systematic human observation and record-keeping. Astronomy is the oldest science precisely because the dark sky demanded explanation from the first minds capable of asking questions. The darkness itself, the black background against which the stars appear, was a profound mystery for most of human history. What is the darkness? Why is there darkness at all if the universe is filled with stars? These questions did not have scientific answers until the 20th century. They were answered instead with myth and metaphor. The sky is a dome with stars as holes through which celestial light shines. Or, the sky is the body of a deity. Or, the darkness is the primordial void from which creation emerged. The scientific answer, finite age, expanding space, cosmological redshift, is more strange than any myth. The darkness is not absence. It is the edge of the observable universe. It is the invisible microwave glow of the hot early universe, stretched to invisibility by 13.8 billion years of cosmic expansion. It is depth, the depth of cosmic time and cosmic space, extending to a horizon defined by the age of the universe and the speed of light. Knowing this changes what the dark night sky means, not in a way that diminishes the experience, in a way that deepens it. The darkness between the stars is not nothing. It is a boundary between the knowable and the unknowable. It is the cosmic horizon beyond which the universe extends in ways that light has not yet had time to inform us about. It is the accumulated history of the universe, encoded in the specific brightness and spectrum of the background. Every clear night, the sky demonstrates the resolution of a paradox that took centuries to understand. Every dark patch between the stars is the answer to a question that confused Kepler and Halley and Olbers. The darkness is the proof that the universe has a beginning, that it is expanding, that the finite history of stellar emission is insufficient to fill the sky with light. Light pollutes most of the night sky visible to most humans today. Artificial lighting from cities has washed out the stars in most of the inhabited world. The Milky Way is now invisible from approximately 1/3 of the world's population, and barely visible to another third. This loss of the dark night sky is one of the most significant cultural and scientific losses of the modern era. A loss of connection to one of the oldest and most universal human experiences, and a loss of the sky as a scientific resource for ground-based astronomy. The darkness of the night sky, the specific darkness that resolves Olbers' paradox and demonstrates the finite age and expansion of the universe, is something that most of the world's population cannot directly experience anymore. The night sky that inspired the first astronomers and shaped the mythologies of every civilization is disappearing behind a permanent glow of artificial light. This makes the experience of a truly dark sky, in a desert, in a remote mountain range, at sea far from land, increasingly rare and increasingly valuable. The experience of seeing the Milky Way blazing overhead, of counting thousands of stars, of watching the sky rotate slowly through the night as the Earth turns. This experience is becoming a privilege of location and effort rather than a universal human birthright. The paradox that the sky is dark while stars are everywhere is resolved by physics. The paradox that most people now live under skies too bright to see those stars clearly is resolved by sociology and politics, by choices about artificial lighting, by recognition of dark skies as a resource worth protecting, by efforts to reduce light pollution in ways compatible with human safety and activity. The darkness of the night sky is both a physical fact about the universe and a fragile human heritage. The physics will remain. The universe will continue to be finite in age and expanding in space, regardless of human activity. But the ability to experience that darkness directly, to look up on a clear night and see the specific dark sky that resolves Olbers' paradox, to have the experience that every human had for hundreds of thousands of years before artificial light, that experience requires effort to preserve. The stars are everywhere. Space is dark. And the darkness, fully understood, is one of the most profound facts we know about the nature of the universe we inhabit. Go outside on a clear night. Find a place dark enough that you can see the Milky Way, away from city lights, away from the orange glow on the horizon that most people now live permanently beneath. Let your eyes adapt. Wait 15 minutes for your pupils to dilate fully and your rod cells to reach their maximum sensitivity. Then look up. What you see is a paradox that took humanity 350 years to resolve. Stars everywhere, thousands of them, points of light in every direction, the Milky Way a band of unresolved starlight stretching across the sky, the Andromeda galaxy visible as a faint smear to the naked eye, an entire galaxy of 1 trillion stars at a distance of 2.5 million light-years, appearing as a small fuzzy oval. And between all of it, blackness. The dark background against which every star is a bright point, every galaxy a faint glow. Not grey, not dim, black. This blackness requires explanation. The universe contains a septillion stars. They radiate in every direction continuously. The light from all of them is travelling through space right now in every direction, including toward your eyes. Why is the background between them black instead of as bright as the surface of a star? The answer is the history of the universe told in darkness. The universe is 13.8 billion years old. Light travels at a finite speed. Light from objects more than approximately 46 billion light-years away, accounting for the expansion of space during the journey, has not had time to reach you. The observable universe is finite. There are enough stars in it to produce bright points of light scattered across the sky, but not enough, and not distributed in a way that every direction of sky is covered by a stellar surface. The universe is expanding. Every galaxy beyond the local group is receding, its light redshifted to lower wavelengths and lower energies by the expansion of the space through which it travels. The most distant sources have their light stretched by factors of 10, 100, 1,000, shifted from visible wavelengths into infrared, into microwave, into radio. The energy that would brighten the sky arrives at wavelengths your eyes cannot see. The hot early universe, the plasma that filled all of space for the first 380,000 years, glowed like a 3,000 Kelvin furnace. That light is still here. It is filling the entire sky in every direction, simultaneously, right now. But 13.8 billion years of expansion have stretched it into microwaves, completely invisible to human vision, but detectable by radio telescopes. The entire sky is glowing in microwaves. You are bathed in the ancient light of the Big Bang right now, and you cannot feel it. These three facts together, finite age, expanding space, redshifted early universe, explain why you can stand under a septillion stars and see black sky between them. The universe is not old enough or dense enough or transparent enough to fill every line of sight with stellar light. The light that exists is mostly at wavelengths you cannot see. The observable universe has a horizon, and beyond that horizon, darkness is not absence, but inaccessibility. The black patches between the stars are not empty. Every one of them contains galaxies, thousands of galaxies per square degree visible in telescope images. Each galaxy containing billions of stars. Each galaxy seen as it was billions of years in the past, because of the time it took their light to reach you. The blackness is depth. It is the observable universe extending backward in time through 13.8 billion years of cosmic history, growing fainter with distance and redder with expansion until it fades below detection. And filling all of it, every dark direction, every bright direction, every cubic centimetre of space inside your room and outside, and in the depths of intergalactic space, the microwave glow of the early universe. 2.725 Kelvin. Invisible. Present. In every direction simultaneously. The oldest light in the universe, the afterglow of the moment the universe became transparent, stretched by cosmic expansion from orange-hot visible light to cool microwave invisibility over 13.8 billion years of travel. The darkness is not the absence of light. The darkness is the universe seen at visible wavelengths through a finite age expanding space with a specific history of star formation. Change any of those parameters and the darkness changes. Make the universe eternal and the sky blazes. Stop the expansion and the sky brightens as distant light accumulates without redshift. Make star formation more efficient and the background brightens. The specific darkness of the specific sky above you tonight is a consequence of the specific universe you inhabit. And the specific universe you inhabit has one more property that the darkness reveals. It is young enough and expanding fast enough that its future is darker than its present. The accelerating expansion driven by dark energy is already pushing galaxies beyond the cosmological event horizon, already making them permanently invisible. In hundreds of billions of years, all the galaxies you can see tonight, beyond the local group, will be gone from the sky, receded beyond the horizon, their light arriving never again. The night sky will be darker then. The stars of the local group and its merged remnant will shine against a sky with no external galaxies, no CMB glow at detectable frequencies, no evidence of the larger universe that exists beyond what dark energy has placed beyond reach. The dark sky tonight is therefore not the minimum possible darkness. It is an intermediate darkness, darker than the young universe that glowed with plasma and the first hot stars, lighter than the old universe that will have lost its galaxies behind the expanding horizon. We see the sky at a specific moment in its history, the moment of maximum cosmological richness, when the universe is old enough to have built galaxies and planets and life, but young enough that those galaxies are still visible, still observable, still sending their ancient light through expanding space to arrive at your eyes. You are standing in a specific moment in the history of the universe. The dark sky above you is what that moment looks like from the inside. The blackness is the universe's age. The stars are the universe's productivity. The Milky Way is your home in it. The faint smear of Andromeda is your nearest large neighbour. The invisible microwave glow is the universe's origin. All of it, the darkness and the light both, is the answer to a question that confused the greatest minds for 3.5 centuries. Why is space dark if stars are everywhere? Because the universe began, because it is expanding, because the ancient light has been stretched to invisibility, because the observable horizon is finite, because you are looking through the entire history of the universe simultaneously and seeing it as it is, vast, dark, punctuated by light, bounded by a horizon defined by the speed of light and the age of time. Go out, look up, let your eyes adapt. The darkness between the stars is not nothing, it is the answer.